Hello, I just want to do a video because I've had a number of people ask questions about the new work at the alkenes 2 mechanism. So I'll do this, I'll put it on, and anybody who has been struggling who's contacted me, then I can give an extension. Now, going back to the alkenes 1 mechanism, the thing that we were looking at, whether it was ethene, which looks like that, or butene, which looks like that. Now, it doesn't matter in either case of this, we were adding a halogen, and a halogen like Cl2 or Br2, I'm not going to go through the whole mechanism. So if we added Cl to that, or Br2, Br to that, that chlorine is going to go there, the other chlorine is going to go there. And it doesn't matter if that chlorine goes to that one and that one goes to that one, or so doing it the other way around. So whether that one goes to that carbon and that one goes to that carbon makes no difference. With this, what we're always going to get remember, this isn't the mechanism, I'm just quickly going through the going to the products. We end up with that, one of each of the atoms on each of the carbons in the double bond, and we get the same with this. Right, so that's the basic theory of reactions with alkenes. Whenever you're adding a molecule to it, one bit of the molecule will go on one of the carbons in the double bond and the other will go on the other carbon in the double bond. Right, that was essentially it off the first alkenes mechanism video. Now the one question that I posed to you right at the very end of that was with propene, and I can't remember if it was bromine or chlorine reacting with that. Now we'll show this in its entirety. Now, unlike these two, both of these here have a line of symmetry down the middle of the double bond. Propene doesn't do that. What that means is, in the context of the first mechanism's work, is that if we've got bromine reacting with that, so I'll show the full mechanism this time. So the double bond attacks the 1Br, and then that bond breaks to go to there. Now we've got an option with this. That Br, that first one, has two options as to where it's going to bond onto. Now the first option is if I put it on the first carbon. That makes that as the carbocation intermediate. The other option is if I put that one on the second carbon. And we get that. Now, I've seen a lot of you have figured this out, and that's not a problem. Now, ultimately, we end up with the final step of the mechanism, where that will attack the carbon with a positive charge. And in both cases, we still end up adding, ultimately, a bromine onto that carbon and a bromine onto that carbon. So we're going to end up with, make sure you can see that. we end up with just one product. There's no difference with that, and that's because we're adding a bromine to one carbon in the double bond and we're adding another. The point of this, why I asked this at the end of the first alkenes mechanism, is that yes, we end up with one product, but there are two potential carbocation intermediates. And that was an introduction to the fact that we get those. Now, when you're reacting the alkene with a halogen, you always just get one product because you're just adding a Cl to one carbon and a Cl to the other carbon in the double bond. Now, going on to the next alkenes mechanism, so part 2 of it. This time we're reacting firstly with a hydrogen halide such as HBr or HCl, and secondly with sulfuric acid. Now, the point in this comes down to whether you've got a symmetrical alkene like ethene or butene, or whether you've got an asymmetric, so non-symmetric, and that may be propene or butanone. Right, so if I take a symmetric, so ethene plus HBr. Right, so I will show the full mechanism, which is what you're supposed to show. So, electrons in the double bond attack the H atom. It's delta positive. You can show it if you wish, you don't have to. So that attacks that, and then that bond breaks. Now, if you recall, just going back to this one, an asymmetric alkene led to the potential of having 2 carbocations, because here it's a 3-carbon chain. We could have the positive charge on the first carbon, like this one, or we could have the positive charge on the second carbon, like that one. If you've got a symmetric alkene, so let's just break that carbon to carbon bond, that double one, turn it into a single, flatten the 2 H's. If I put that H on that one and a plus on there, is that actually any different to doing it that way around? No, it's not. These two are the same carbocations. It's just that to go from this one to get to that one, you've just flipped the molecule over. So I don't need to worry about that one. And then we end up with that. So if it's a symmetric alkene, symmetrical alkene, we get only 1 carbocation possibility, and only 1 product. So it doesn't matter with the symmetric alkene if I put the positive charge, on the first or second of the carbons in the double bond. The molecule started off as being symmetric across there. It makes no difference. The relationship between putting the positive charge on the other carbon just means the molecule just flipped over. Right, now let's do an asymmetric. So propene. Propene plus HBr. Exactly the same structure to the mechanism, no changes in the curly arrows. But as you can see, it's not symmetrical across the double bond because we've got that there. So I can either put that H bonding onto that carbon, or I can put the H bonding onto that carbon, but they're two different structures. So I'm going to show the mechanism for the H bonding onto that one first. So let's just draw it out, breaking the double bond. So I'm going to put that one on that. That becomes the plus. The plus is on the second carbon. And the Br minus comes in and attacks that. And that will be 2-bromopropane. Notice it's propane. A number of you put that down as propene. It's gone from an alkene, but now it's an alkane because it's got single covalent bonds. But it's also got a halogen atom where the 2-bromo comes in. Now the other alternative, and I'll do this as a separate mechanism because this is how I wanted you to show it. So exactly the same first step. Electrons in the double bond attack the H. The bond between the H and the Br breaks towards the Br. And this time, instead of putting the H on that first carbon, I'm going to put the H on the second carbon. So let's just draw the flattened out starting molecule. And this time that H is going to bond onto that carbon. So the plus is on that one this time. Also, don't forget, a number of you have been forgetting to put the lone pair of electrons on this Br minus at the end here. And make sure it's attacking the carbon, not the plus. So this time I get, as you can see, so this time the bromine is on the first carbon in the 3-carbon chain. So that's 1-bromopropane. So we've got two products. So an asymmetric alkene, that gives us two possible carbocations. And therefore two different products. Now the final bit about this is these products aren't made in equal quantities. And that's because one of these carbocations is more stable than the other. So the more stable the carbocation intermediate, the longer it will last, and the more there's a greater chance of the Br minus colliding with it to make a product. And in the notes I told you the way to determine which one is the most stable out of the two carbocations is to look at how many carbons the C plus is directly bonded to. So in this one, this C plus, I don't want to draw a curly arrow. That C plus is bonded to two carbons, one there and one there. But in this one, the C plus is only directly bonded to one. We don't count the one further down the chain. That C plus is only bonded to one carbon. So C plus is only bonded to one carbon. That makes this one, this carbocation, the more stable. This carbocation is the less stable of the two. Therefore, this product is going to be our major product. This one is going to be our minor product. And that was the other thing that I needed you to determine. Now, the only other thing that you need to do is involving sulfuric acid. So remember, I've shown you the structure of sulfuric acid. And when you've got your double bond with all of its bits and pieces there, remember from the double bond to the H, and then that bond breaks. And then when you've got your intermediate step, so you will have, what is really simplifying this, you'll have hydrogens and carbon atoms coming off this structure. There'll be a plus somewhere, and then the remainder of that, O, S, it has a lone pair of electrons, a negative charge, and that attacks the carbon. But you still have to bear in mind the same things that I've just gone through. If you've got a symmetric alkene, that will give you one possible carbocation intermediate, one product. If you've got an asymmetric alkene, that will give you two possible carbocation intermediates, therefore two different products, and one will be a major product, one will be a minor product. Okay, thanks a lot. Get in touch with me if you have any more problems with this.